Hi guys, welcome back. So today what we're going to do is we're going to introduce the idea of electric potential energy and how it's additive. So here we're going to use this idea. So I have three formulas right here, and we have the electric field for a point charge, the electric potential for a point charge, and then the electric potential energy for a point charge. So as you can see here, the difference between the electric potential and the electric potential energy is you just have an extra Q right here, an extra charge. That's all it is. So basically, we can also write this as Q times V, because V is just another charge times K over R. So this is also an equivalent form of electric potential energy. So now the idea is, let's say I brought in, let's say I had a system of 4-point charges at each corner of this square. Oop, that's not a charge, right? We had 4-point charges at each corner of the square. And wow, and each side has a length of s, right? S. So an AP question would most likely ask, what is the electric potential energy of this system? So to deal with this, we actually have to go back in time, right? So let's say what we did is we brought all these charges for a faraway place and then calculate the potential energy of each time we brought a charge. So I'll show you how to do that. Just erase these real quick. I don't really care about that gray space. So let's say I brought a charge infinite from a far distance plate, right? Infinite. Let's say I brought it from infinity all the way here, all the way to this place right here. Okay. Now, what was the work or the energy it took to bring this charge, this one charge particle, to this corner? So here we can start writing our U of system. Actually, we'll just do with the first one, right? Let's start with the potential energy of the first charge. Did it take energy for me to bring this particle from infinity to here? No, it actually did not take any energy, right? I'm not fighting against any other force, right? I'm not fighting against any of the charges or any of the fields. I'm just simply pushing a charged particle this direction from infinity to where it is right here. So right now, potential energy of the first charge is 0. Now let's say, just for this system, all the charges are Q. They're all the same. Just to emphasize that they're all Q. This can be done with different charges, right? It can be done with different charges with different um, charge on them. But for now, we're just going to keep it relatively simple, right? So now let's say I brought another charged particle all the way from infinity, all the way, here, right? Now here we have to wonder whether or not this is 0 or did it take energy to bring this? Well, it did take energy, right? I'm fighting against this one, right? Since this is a positive charge, right? I'm fighting against another positive charge that wants to push away, right? Because this is a repelling force. This wants to push away this charge from entering this system. But it took work against me, negative work, to bring this charge from infinity all the way here. Okay? And we know that negative work is equal to positive potential energy. So this took positive energy. This increased the potential of the system. So how would I calculate this? Well, first, we just do the electric potential energy, right? We have this electric potential energy times Q right here. This formula right here tells you the potential energy that was increased in the system when I brought this charge. So U2 would just equal Q squared, right? Because I have two Q's. So Q squared times K over S. That's what potential is, right? That's how much energy it increased in the system when I brought this energy from here. When I brought this charge all the way from infinity. Okay, so then what about if I bring a third charge all the way from infinity all the way over here, right? Again, it doesn't really matter the path I take for which, because uh, the electric force is a conservative force, the same as gravity. It doesn't matter; it's path independent. It doesn't matter the path it takes, just the starting point and the ending point. And we know the starting point is infinity, and the ending point is right here at this corner. So this corner right here, we have another q plus, right? So now the question is, how do you calculate the potential energy if I have two different charges acting on it? Well, then you just take the potential energy of each of the separate charges and then add them together. So let's say we have U of 3, right? So this is going to be, we're going to have to take the potential energy or the energy that was increased to the system when I brought the charge close to this charge, and the potential energy from this part of the system when I brought it to this charge. So let's calculate that real quick. Let's see. Let's say I did it with this charge real quick first. So here we're going to have Q squared, right? Because I have two Q's, and then I have to multiply by K, and then the distance between these two is S. Okay, that's great. So we got that one down. So what about this, right? Well, let's work it out, right? We know it's Q squared again because there's two charges. We know it's always multiplied by a constant K, or 1 over 4 pi epsilon naught. But now, what is it? We have to figure out what the distance is, because distance is not S, right? Distance is, in fact, this diagonal between the square, right? It's not going to be S, because S is just this horizontal thing. So what's the distance? Well, using our famous Pythagorean theorem, so when we have both of these right here, right? We know that's a squared plus b squared is equal to c squared. We know that this is equal to s squared plus s squared is equal to c squared. And we know that this is going to be 2s squared, which is equal to c squared. And I take the square root, right, of both sides to get my c, or which is this is c. Then I'm get root 2, bring out the s squared because the square root is, so s root 2 is equal to c. So the distance between these two charged particles is going to be s root 2. So now we found the distance is going to be s root 2. So now we have found the potential of the electric potential energy of this charge right here, this third charge, or the electric potential energy that was increasing the system when I brought this third charge over. Okay, so now we have to do the fourth charge, right? I'm going to, again, bring another charge all the way from infinity, wrong color, all the way from infinity to here, right? So that's going to be Q plus again. So now we do the exact same thing that we did with the third charge. We just have to do it with an extra charge, right? So we're going to have the potential energy from this charge, potential energy from this charge, and the potential energy from this diagonal, right? So let's do those all three together, right? So U4 is equal to, well, we'll do this one first, right? So it's going to be Q squared K over S, right? Because it's just this S length plus another Q squared K over S, right? Because now I'm adding this charge over here. So Q squared K over S plus now I have to also add the diagonal of this one. And since we already found the diagonal for the other one, it's the same diagonal because we're in the square, right? So the distance between these two is still going to be S root 2, right? So now we have all of these added up together. All we have to do is add up all these potential energies to get the total potential energy in the system. So let's do it together, right? Know that we have 1, 2, 3, 4 q squared k over s, and then we have 2 q squared k over s root 2. So I'm going to do the 4 q squared k over s. I'm going to add these two plus 2 q squared k over s root 2. And that will be the potential or the electric potential energy of the entire system, of this system, as of right now. Again, you can do this with any shape. For example, let's say we brought a triangle over, right? Let's say um, you had a triangle like this, and this was S, this was S, and this would have to be S root 2, right? Using Pythagorean theorem and the law of triangles for 45, 45, 90-degree triangles. And then we had Q's here, Q. But let's say this was 2Q, right? And this was 3Q. Now what would be the potential of the system? Well, again, you just pretend you first go back in time and see the energy it took to bring each charge into that place. So let's say we have infinity here. What I suggest is you remember that this is taking it all the way from infinity to this place, right? We're taking it from, that's our reference points. Infinity is known as our reference point. All right, so I bring a charge all the way from infinity to here, right? Charge of Q plus. Okay, so that's going to be U of 1. The first charge will always have a potential energy of 0 because it took no energy, it took no work to bring that charge there. I'm not fighting against any other forces. So U1 is equal to 0. What about U2, right? So I brought another charge all the way to here, and this charge is going to be 2Q, right? So it's the same thing. It's going to be U of 2 is equal to, you just multiply the two charges together. So 2Q times Q, multiply the constant, and then the distance between each other, which is going to be S. All right, and then I brought another charge all the way from infinity. It'll be right here. This is going to be 3Q plus. Again, these are all positive charges. And the idea is now we just add the distance between these two as well, right? So it's going to be U3 is equal to, we'll do these two right here, right? So that's going to be 6Q squared, because I'm multiplying these two over, multiply the constant, and then over the distance that they're separated, which is S. Then I have to multiply, I have to do this one. I have to do this part. I have to, so now I multiply these two together. So this is going to be, what am I doing? Not 4. 3Q squared K over S root 2. Okay. So now all we got to do is add these up together to get, excuse me, the potential energy of the system. So again, we're gonna have, it's gonna be 2Q squared, which let me just rewrite that so it's easier to add. 2Q squared plus 6Q squared, that gives me 8Q squared K over S plus this term, 3Q squared K over S root 2. And actually, we can take a lot of these things out to get one simple answer with all the things out. So then we have Q squared K over S times 8 plus 3 over root 2 is your answer for the potential of this system. Hope you guys enjoyed this video, and as always, learn. Have a good day.